So today, Andrey Smirnov will give his last lecture of the M-seminar mini course on Frobenius structure for quantum differential and Q-difference equations. So, Andrey, please.
Right, thank you. So let's continue. And today I would like to start with the following very explicit example. So let's look at this 2x2 matrix. It depends on a few parameters. It depends on parameter z, parameter a1 and a2, and parameter h bar. So secretly, what this matrix is, it's an operator of quantum multiplication by line bundle O1 on the Nakajima variety given by cotangent bundle over projective space. And so this matrix is a quantum multiplication by O1 in a certain basis in the K theory of X. So namely, I guess it's written in so-called stable basis. Doesn't really matter what it is. So parameters in the story here. So h bar, a1, and a2 are equivariant parameters. So h bar is as before. It's a parameter which scales the cotangent fibers and retracts everything to p1. And a1 and a2 are parameters of certain torus which rotates p1. And z here is a Keller parameter, so it's a parameter which counts degrees of degrees in quantum K theory. Well, this parameter z is usually denoted by q in quantum cohomology, but for us q is something else, so here I denote it by z. So z is the same as degree counting parameter. So it's easy to check, say, substituting this matrix to a computer and verifying that it satisfies this relation. So this relation, of course, is some quadratic polynomial for matrix M. So it's nothing but the characteristic polynomial for matrix M written, in this funny form. And this relation is actually nothing but the relation in the quantum K theory ring of this variety. So in fact, the quantum K theory ring of X is generated by M with only one relation. And so this is exactly the relation in quantum K theory, in equivariant quantum K theory. All right. So, but now let's do the following thing. Let's pick a number, a natural number p. Well, and I'd like to emphasize that here today p does not have to be a prime number, at least for maybe a half of the stock. And let's choose pth root of unity. It may be a complex pth root of unity or, whatever field you are working with. And we can define the following thing, which is some kind of average of this matrix with respect to shifts of the Keller parameter by the roots, right? So it's mz multiplied by m shifted by the root and so on, and all the way up to, so basically all roots of degree p appear in this product. So the claim is that this new matrix, so it's again some 2x2 matrix, it satisfies Frobenius of this original relation. So what do I mean by that? So there is the following theorem that this averaged matrix MZ satisfies the same relation as before, but now each variable, like equivariant parameters and Keller parameter in this equation, is raised to the power p. And well, if you think about it, first of all, that's not obvious at all. Well, simply because values of m and m shifted, they do not commute, so we cannot really, diagonalize these matrices in one common basis and then, understand what happens with their eigenvalues. And second is that if you just take a random matrix M with some rational coefficients and Z, it doesn't true that characteristic polynomial of this matrix and its average, that characteristic polynomial of averaged by roots matrix comes as a Frobenius of the characteristic polynomial for M. So there is something special about this matrix M. And, the reason why it's true, I guess it's geometric. So it's not a random matrix. It comes from geometry. Well, again, this is, again, simply the characteristic polynomial of this. And by the way, I already forgot that I need to put this this index zeta here everywhere. So it's this averaged matrix. It's not the original M. All right. So it follows that if you have eigenvalues of your original matrix, then the eigenvalues of...
Just a second, since you added the index here, so this A1, A2, and that was in the previous star for MC. Is that the same A1, A2?
It's the same A1, A2, yes. So
yeah, the original star for MZ. Okay.
Yeah.
Thank you.
Yeah. And so eigenvalues of this averaged matrix are the same as eigenvalues of M. And again, you just need to raise all variables to the power P. Well, and the other way to say that is that the matrix, the averaged matrix, and the original matrix in which all variables are raised to the power P are isospectral. And again, this is not obvious identity, but that is true.
Andrey, why do you call it Frobenius if P is no longer a prime number? For me, it looks more like that Adams operations on a certain ring. So.
Exactly. Yes. So maybe it's better to call it Adams operation, and in a sense, maybe a proper name for this guy, for this averaged guy, some kind of quantum Adams operations.
Okay.
Mm-hmm. All right. So I have this thing, and I'll try to explain why it happens. And it follows more or less from our previous discussions. So first, I'd like to explain what is more general version of this thing. So let me first explain how this matrix M come up.
Sorry to interrupt you. So if P is not a prime, so the order of Kasai P may not necessarily be P minus 1. Do you want to take the Euler function phi of P or just take P minus 1?
Here I mean the primitive root of this order.
Yeah, it's a primitive, but if P is not a prime, so the multiplicative order of the primitive root may not be P minus 1. It's much smaller.
No, but by this primitive, I mean that, the order of this root is exactly P. So it's not true that it's a smaller power is 1. So this is the root I want. So I want to have a root of order P. Mm-hmm.
Okay, thank you.
Mm-hmm. Okay, so first let me just make a small detour to quantum K-theory of Nakajima varieties. So Nakajima varieties, they by definition come as GIT quotients of some vector space well, you have a quiver, you have representation of a quiver. So this is a representation of a quiver, and you take a JIT quotient with some stability parameter. But you may always think that this guy is sitting inside the categorical quotient as some open subset in this stack, and then maps from the curve to the stack, which generically land in this open subset. So maybe for all but finitely many points on this curve, you land in the stable locus here. So you land in X, and at some point it's allowed to be it's allowed that the values are not stable, and those points are called singular. And so the maps like that with finitely many singularities, they called quasi-maps. And it's known that the moduli space of quasi-maps, well, they're very nice. So there exists some moduli space of these quasi-maps with some extra boundary conditions, which can be imposed at finitely many points on your curve. Usually it's called relative conditions, and it's a long story to discuss what relative condition is, but maybe for today it's not that important. So we have this moduli space, and it's equipped with some structures. First of all, we have some virtual structure sheaf on this moduli space, and we have evaluation maps for each of these relative points. So roughly speaking, this evaluation map take a quasi-map and sends it to the value at this point P. And it's known that for this relative boundary conditions, which means that your moduli space is compactified in a certain way. And so this compactification results in the fact that these maps are proper, and we can compute like push forwards of this virtual structure sheaf, and those push forwards will be like integrations over that moduli space. So we can compute some kind of Gromov-Witten invariance. So, using the structures, we can define the following thing. We can take a class, K-theoretic class, and we can consider a moduli space with 3 relative points, and we can define the following integral. Well, by definition, it's the following thing. You take one of the points, say P3, and you use it to pull back your class from X to the moduli space, right? So you use the evaluation map to pull it back. Then you tensor it with a virtual structure sheaf, and you use the rest of 2 points to push forward the result back to X. So by definition, what you get some element which lives in the tensor square of equivariant K-theory. So it's like a matrix, right? If you choose some basis in the K-theory, then you get a matrix in this basis, and its matrix elements are power series in this variable Z, right? So again, when we compute this push forwards, you also organize them into a generating function, and Z is the degree counting parameter. Well, in fact, it's not actually, it's a power series, but it is also known that the result is a Taylor series expansion of some rational function in Z, actually. So this thing converges to certain rational function. And the example of matrix M from which I started is exactly one example of this construction. And well, by definition, quantum K-theory ring is the ring of these operators. So it's a ring generated by these guys M. And yeah, so this is an element in the tensor square of K-theory. But on the K-theory of Nakajima varieties, there exists a pairing which is non-degenerate, and so you can use this pairing to understand this matrix as a linear operator. So it's like an operator acting on K theory. All right. So yeah, and quantum K theory is a ring generated by these operators. All right. Then we know geometrically we can show that this ring is commutative, and behind that there is certain procedure which is called degeneration and gluing. Roughly speaking, the situation is the following: that if you have if you study partition functions with 4 points, then the order of these points on the rational curve doesn't really matter. So we can switch the order of insertions tau1, tau2 in this way. And then the result doesn't depend on degeneration. So we can degenerate this rational curve to a sort of nodal curve, which consists of two rational curves, which with one nodal singularity. And then computations of Quasimap from this thing give you a product of M operators in one order, and in this way, M operators in the other order. And so you can use that type of formalism to prove that the ring you construct is commutative. And then for Nakajima varieties, there is a conjecture. I'm not really sure what's the status of it now. I guess in some cases it's proven, but in general still not. Is that this the quantum K theory? So I guess it should be Q here. Quantum K theory is generated by finitely many elements given by quantum multiplication by tautological line bundles. So every Nakajima variety is equipped with a set of tautological line bundles. The number of those line bundles is the number of vertices in your quiver. And so the conjecture is that the spectrum of this, the joint spectrum of these finitely many operators is simple. And so they actually generate everything. All right. So, and slightly more general version of example from which I started claims that the above mentioned isospectrality theorem holds for all quantum multiplication by these tautological line bundles. So namely, if you start with, again, with the, I don't know, some kind of averaged operator of quantum multiplication by line bundle L, and you also look at operator in which all variables are raised to the power p, then these two are isospectral. And moreover, we will show that there exists some kind of transformation, which may be called Frobenius transformation. So it's some operator acting on K theory, which conjugates one of these operator to another. All right. And again, this is probably the good name for it is maybe a quantum version of Adams operations. And the reason for that is because when I just note here that when z is equal to 0, so you turn off all quantum correction, this operator is just L. So it's just an operator of classical tensor multiplication by L. And so it means that this averaged operator, zeta p, at 0 is exactly L raised to the power p. And so classically, this operation is exactly the Adams operation. It's an operation which acts on line bundles, raising them to the power p. And this is some kind of quantum generalization of this thing. All right. Well, let me explain a sketch of the proof of that theorem. So the proof goes like this, and again, the central point in the proof of this result is again some Q difference equation associated with Nakajima variety. And well, this Q difference equation arises as follows. In this theory of quasi-maps, we can also construct a moduli space of quasi-maps from P1 minus infinity point. So it's like a disk. So you study quasi-maps from a disk C to X. And C is P1, your rational curve, minus the point infinity. Well, this moduli space, again, is equipped with a couple of evaluation maps at 0 and at infinity. But there is an important difference, is that the map at infinity is not proper anymore. So you cannot really do push forwards using this map. But it becomes proper if you consider an action of extra torus, which I denote CQ here. Well, this torus acts on the source of the quasi-map by rotation, so it rotates this disk, exactly fixing the point 0 and infinity. And the action of this torus on a curve induces the action on the moduli space. And it's known that the evaluation at infinity becomes proper if you restrict it to the set of fixed points. So, which means that we can still compute push forwards with evaluation at infinity using equivariant localization. And well, in particular, we can define the following power series, which I call psi here. So it's an evaluation of a virtual structure sheaf on this moduli space at 0 at infinity. And again, you organize this push forwards into a generating function. It's a sum over all degrees of quasi-maps, and you weight degrees with parameter z. So again, the result lives in a tensor square of K theory. It's a power series in Z, so it's like a matrix. Again, in some basis, it's going to be given by a matrix with coefficients given by power series. And now it's a localized K theory, which means that coefficients of your power series, they will have some, there will be some rational functions in this parameter Q. In particular, they will have poles of the form like 1 minus Q to the power n. And in principle, this pole may appear for all possible n's. Right? So again, it's the result of this computation, as I mentioned last time, for some viewer varieties like type A Nakajima varieties, we can compute matrix elements of this matrix quite explicitly, and they are some kind of generalizations of Q hypergeometric series. So if you know what Q hypergeometric series is, you know exactly that it's the coefficients feature this type of denominators. Well, anyway, so in particular, these functions cannot be in general evaluated at Q is equal to 1 or at Q given by any root of unity, so they're singular at those points. Well, if you apply this degeneration and gluing formalism for these quasi-maps from disk, you can prove the following thing. So roughly speaking, the situation is depicted here. So you insert additional descendant at some point, and then you can use the generation to rewrite this partition function as this type of products. And the result is that, one partition function is equal to original partition function with scalar parameter shifted by some power of q, which I denoted here by q to the power l. Well, it depends on the insertion. And on the other side, you have exactly this part is the quantum multiplication by this m times the original partition function z. So this computation, which is sketched here, very, very roughly speaking, gives the following result, which is due Akhenkov originally that psi, this partition function, is the fundamental solution matrix of certain Q-difference equation. So this is a Q-difference equation I also mentioned last time, but this is how it appears geometrically. And this quantum difference equation says that, well, if you shift scalar parameter by some power of q, then the result is that your partition function is multiplied by by operator of quantum multiplication by this line bundle L.
What means q in the power line bundle? I'm confused.
Yeah, so here, maybe I should explain it. In general, you have pcar, maybe I'll write it here, pcar of x is generated by tautological bundle for Nakajima varieties, and it's a lattice. So it's a lattice L to the power L. In particular, here you can choose a basis of tautological line bundles. Let's call it so there is a basis of tautological line bundles, and then any line bundle L can be written in the basis of tautological line bundles as maybe L1 to some integral power N1, and then L to the power NL. So any line bundle has this form where the components are tautological line bundles. Now, Z to the power Z, Q to the power L means the following. So in general, we don't have one scalar parameter, we have several. And so we have Z1, Q to the power N1, ZL, Q to the power NL. So this is the notation for the shift by line bundle L. Okay?
Okay.
Mm-hmm. All right. Yeah, so this is just denote some shift of scalar parameters. This is just a notation. Okay. What's next? Yeah. So now the proof works very simple. So let's look at this quantum Q-difference equation, which I denoted by star here. Then we can do with it two things. First, we can just formally take this Q-difference equation and raise all variables to the power p. Right, then you have this fundamental solution matrix in which all variables are raised to the power p, and it satisfies, some induced Q-difference equation with a matrix M in which also all variables are raised to the power p. Or, so you can do this thing, or you can do a different thing. You can take this original Q-difference equation and iterate it p times. So instead of, it's like you shift not by q, but q to the power p. And so if you iterate this Q-difference equation p times, then shift by power q to the power p results in this product of M matrices. And, well, you can note here that, what is written here, this iterated product of n matrices at q given by zeta p, by this root of unity, is exactly the matrix M Z, which I denoted M zeta p z. So somehow I want to show that the spectrum of this operator here and the spectrum of this iterated product at Q given by pth root of unity coincide. Well, and now it's simple. What you do, you simply divide first equation by the second. And then you note, and this is what we discussed maybe last time, or maybe in the first, in the last two talks, that this ratio of fundamental solution matrices, this is exactly what we called Frobenius structure. Well, it's what you can show that this thing is well defined at pth root of unity. So even though these guys have poles, this at the root of unity, in the ratio there is no poles; they somehow cancel out, and so this thing exists and it's well defined. And if you divide one equation by another and restrict everything to q to the power p, you exactly get that this operator u is an operator of similarity. So it's a gauge transformation which conjugates one operator into another. So we constructed an explicit gauge transformation which transform one operator into another, so they have the same spectrum, and moreover they're similar in the sense that this gauge transformation exists. And this gauge transformation is exactly what we called Frobenius structure in the previous talk. So this is roughly speaking how this proof works. Okay. Well, the next part is the following. So we can we now prove this isospectrality theorem. Let me go back. So we can show that the spectrum of this iterated product and the spectrum of the original M, in which all variables are raised to the power p, the same. And we can ask, is there like a cohomological version or cohomological limit of that statement? So this is what I wanted to discuss next. So let's recall from last time that in quantum cohomology of Nakajima varieties, they are governed by certain connection. So let's say this operator, this differential operator, is the operator of quantum connection for some Nakajima variety X. And here operator A, this A here, is the quantum multiplication by a Chern class of some line bundle, maybe it's by some class in the second cohomology. And then there is the following result due to Etingov and Varchenko, which describes the spectrum of p curvature of this connection. So, okay, what is p curvature? By definition, p curvature of connection nabla is the following thing. You take this differential operator, you raise it to the power p, subtract operator nabla, and reduce all coefficients modulo p. Well, again, when I do this, I assume that all parameters, for example, if I study my connection equivariantly, it may depend on a bunch of equivariant parameters, which I denote A here. And I assume that all those are specialized to some rational values. So in particular, I assume that they are all p-adic integers. So this reduction mod p makes sense. So if I have a rational number, if it doesn't have powers of p appearing in its denominator, we understand what it means to reduce it mod p. And so there are some assumptions here. But anyway, so if you understand what it means to take mod p, then you can easily check that if you start from differential operator, this thing, the result is just a matrix. So all this differential, like all these derivatives modulo p vanish. They all happen to be proportional to p, and so they vanish. And the result is that the p curvature is not a differential operator. It's really a matrix with coefficients from the finite field fp. And there is a natural question: so the dimension of this matrix is given by the full dimension of the cohomology of your variety. And then there is a natural question: what is the spectrum of this operator? What is the spectrum of this matrix? And so what Ettinghoff and Warchenko proved, they proved some kind of isospectrality result. They proved that the spectrum of p curvature is related to the spectrum of the original matrix A, so this quantum multiplication by something, as follows. You take this matrix A, you raise all variables to the power p and multiply it by s to the power p minus s. What is s? I probably forgot to mention it. S is like a free parameter which I add in front of my matrix A. So I don't. It's just a variable, so I don't impose any conditions on S. And so, well, this result on the nose look very similar to what we discussed before. This is isospectrality in K theory, and indeed, this theorem is actually a cohomological limit. The cohomological limit of the isospectrality statement, which I mentioned before. So let me explain how this theorem can be deduced from the theorem I mentioned before. Well, for this I need to explain how the cohomological limit works. I guess this is something I also mentioned in the previous lecture. So classically, say over complex numbers, cohomological limit of K theory works as follows. So you replace all equivalent parameters, including Q, by as follows. So you say that Q is very close to 1. And so you say that Q is equal to 1 plus some small parameter epsilon plus maybe some higher degrees in epsilon. And epsilon is a very small, say, complex number. And you can also do the same thing for all equivalent parameters you have. So if you have an equivalent parameter A, you replace it by a similar expansion. So you say that it's 1 plus some small parameter S, small parameter epsilon times S plus, cohomological version of this equivalent parameter, and then higher terms. Then it is known that the operator of quantum multiplication by the line bundle L has the following expansion. So it's again 1 plus epsilon S times this matrix A, which featured in the quantum connection. So here A, again, if you start with quantum multiplication by line bundle L, then this A is exactly the quantum multiplication by the first Chern class of L. So this procedure, which I explained here, basically is like taking, passing from K theory to cohomology is by taking the first Chern class. So it's just a funny way to write it down. And Well, so yeah, this is the connection between quantum multiplication by line bundle in K-theory and quantum multiplication by its first Chern class in cohomology. So in particular, if you look at this Q difference operator, so here Q to the power Z d over dz is just a shift operator. So this operator here acts on functions. So Q, Z, d over dz act on function fz by just shifting z by q. Right, so this is Q difference operator. And then again, if you expand this Q difference operator, then in first non-trivial order in epsilon, that's going to give you your quantum connection. Right. I recall that our isospectrality result holds when Q is a root of unity, pth root of unity. So in order to use all these decompositions, I need to have I need to set Q to be 1 plus some small parameter. And if Q is close to a unit root, then I couldn't really do it over complex numbers, because it's not true that in general for a complex root of unity, one like zeta, this root minus 1 is a small parameter in some sense. But it's actually exactly true if we work with p-adic norms. So at this point, we can switch to considering these operators over p-adic fields and do the cohomological limit, expanding everything close to the root of unity. So how it works? So yeah, so this is going to be true. So when we switch to p-adic norms, so it works as follows. You may start with extension of p-adic field by a certain root, which I call pi, of the following equation. So pi to the power p minus 1 is equal to minus p. So in particular, pi is a small parameter in the p-adic norm. So its p-adic norm, as follows from this equation, is less than 1. So this parameter is going to be something close to my parameter epsilon, right, in the cohomological limit. So it is known that this extension contains all pth roots of unity. And these roots of unity, they have the following form. So their expansion in pi, in this small parameter, start with 1, and then b plus pi, and b can be 0, 1, 2, and so on, all the way up to p minus 1. And this gives you all roots of degree p in this extension. And then, of course, if you take the ring of integers and mod it out by ideal generated by this pi, then you get a finite field. Simply because elements here, they kind of a power series, they look like power series in pi with coefficients which can only be from 0 to p minus 1. And then again, I can use this q. So I'm gonna set this to be q, and so now my q looks like 1 plus something small, and I can do cohomological limit. But I have to be a little bit careful. There's an interesting feature, new feature when you do this expansion p-adically. So you can note that if you have the following expression, like 1 plus s times pi to the power p, and you can expand it up to first non-trivial, first small order in the p-adic norm. So you can know that if you just expand it using binomial theorem, so then in this binomial theorem, the order of the first term and the last term actually the same. Well, simply because pi to the power p minus 1 is equal to p. So p times pi and pi to the power p, they have the same order of smallness, so to say, in the p-adic norm. And so actually, if you do this expansion up to first term in the degree of pi, then the first term looks like this. So it comes from this term here and this term here. So you have to be a little bit careful. So in particular, this type of expressions, s to the power p minus s, show up when you do these expansions. And then having this in mind, we can start with our isospectrality result. So we can start with a matrix M, with a matrix of quantum multiplication by some line bundle L. And you do this expansion over, again, you assume that Q is close to a root of unity, so Q is equal to ZP plus, so it's equal to 1 plus maybe pi, and so on. And you do this expansion over pi, and then in the first non-trivial term, you will find that your matrix, the first non-trivial term in this expansion is exactly the connection matrix. So it's exactly the matrix of quantum multiplication by the first term class, in which all variables raised to the power p. And you have to multiply this matrix by this extra factor s to the power p minus s. Well, the reason why it's up here, I just explained. And you can also do the same thing for iterated product of M matrices, which I can simply write as this Q difference operator raised to the power p. It's the same thing as iterated product. And again, if I restrict Q to the unit root, in the first order in this expansion, which is p to the power p, pi to the power p, you'll find that the answer is nabla to the power p minus nabla. And again, why this appear? It appears for the same reason why this s to the power p minus s appear. It's just you use the Newton expansion and combine terms which have the same smallness. And so we know that the spectrum of this operator and this operator here, when Q is given by the root of unity, is the same. This is our isospectrality theorem. And so by taking the leading terms in this expansion, well, taking the leading terms may be formalized as taking coefficients modulo this ideal. So in particular, you land in the finite field. And so you, after doing all this, you prove that the spectrum of this coefficient here and the spectrum of that coefficient here, if you reduce all the coefficients to the finite field Fp, is the same. And so in this way, we arrive at this theorem of Ettinghoff and Warchenko, which I mentioned. So again, this theorem should be understood as cohomological limit, p-adic cohomological limit at roots of unity of this more general k-theoretic isospectrality result. Okay, so maybe the last thing I will mention, but maybe just by words. There is a interesting recent works of J. Healy, who studied so-called quantum Steenrod operators, and he showed that the quantum Steenrod operators for Nakajima varieties coincide with the operators with the p curvature of quantum connections. And so in particular, he showed that quantum Steenrod operators have the same spectrum as this operator here. And well, in cohomology, quantum Steenrod operators may be understood as cohomological limits of usual Steenrod operators. They can be understood as cohomological limits of Adams operations in K-theory. And so again, this is some kind of quantum version. What we discussed here today is some kind of quantum version of a relation between quantum Adams and quantum Steenrod operators. So namely, this iterated product of quantum multiplication evaluated at Q given by roots of unity can be understood or maybe named as quantum versions of Adams operations. And then in the cohomological limit, we get something which can be named quantum Steenrod operations. And yeah, and so this is maybe also a generalizations of his interesting results from cohomology to quantum K-theory. All right, so I guess it's I finished earlier than I thought, but that's it for today.
Early is okay. It's only welcomed, you know, because it leaves more time for questions. By the way, I remember that when Etingov gave a talk on his work with Varchenko on the seminar, I asked him what about the Q-difference analogs, and he told me that we were working on that or something, and your approach is opposite. You started with the Q-difference result and obtained the result as a limit. Yeah, so then it's so then I assume that your proof is totally different from what they had in mind.
Yeah, but their proof is somewhat, I would say, more general because
it's some pencils of connections.
Exactly, yeah. So it includes these connections for Nakajima varieties as a special case, but I believe they cover more by their methods.
Yeah. All right. Question. I mean, your Nakajima variety is sort of the crucial, at least in your today talk, and in particular, you mentioned this Andrey Akunkov result. But what's indeed is special about, for example, if I take character varieties instead, some sort of multiplicative version, what's the problem? No theorems about fundamental solution. You still can define the counting in this J function and so on. So there is something special about Nakajima.
Well, I believe so. So let me roughly say it. So if you have this K-theoretic, maybe J function of a Nakajima variety, that's going to look like some power series and maybe a bunch of variables, like z1 to the power d1, z to the power dn, and some coefficients here. The coefficients will look like some rational functions and all parameters you have, with some denominators of the form 1 minus q, 1 minus q squared, and so on, and maybe some numerators and other parameters. So in particular, you will see infinitely many poles appearing here at all possible roots of unity. But there is an interesting property of these functions, from which what I mentioned today can somehow be derived, but I don't know how to prove this property. That we can write this J function as a pletistic exponent. Maybe I should write it as S. So it's a pletistic exponent. of something like 1 minus q times some power series in z. So
I assume with some coefficients, yeah.
With some coefficients, but the point is that these coefficients will be already regular at roots of unity, so there is no poles.
Yeah, that's exactly what happened, as you know, in relation of Gromov-Witten to Donaldson-Thomas theory. That's the same phenomenon. Or Gopakumar-Waffa in relation. So you write your answer as platistic exponent, and the coefficients you consider sort of a refined version because you have this Q equivariant parameter, but in unrefined, those coefficients would be integers. That's what people were struggling for. And in refined, they do not have poles. Yeah, it's exactly, I mean, with zero knowledge about left-hand side, I would say that this should be true. Yeah. Okay.
Yeah. So somehow from this property, if you have this property for your like fundamental solution or for this J function, then you can use this to prove that this combination of which I needed. Maybe I'll go back here. Yeah. So this ratio of fundamental solution matrices, even though they have itself poles in all roots of unity, so the pole at primitive root of order p disappear. So you can evaluate this thing, and it's well defined. And you can in principle you can derive this property from what I said here, and conjecturally in examples I know it's always true for Nakajima varieties, and conjecturally that's you know, there is some identity which is behind it, but I don't quite know how to prove. It's actually I don't even I'm not even sure it's proven for, say, Q hypergeometric series, just the basic one.
You see, kind of long ago, more than how many? 15 years ago, when we wrote that paper with Maxim on cohomological whole algebra, so at some point we wanted to prove something which is, I would say, maybe exactly the same, that there are no poles and the coefficients. It's called integrality, whatever. And in the proof we used, well, I would say it's kind of not exactly p-adic methods, but we reduced to use the reduction uh, to all sufficiently large primes. You know, like if you want to prove that something is integer, you use that modulo all sufficiently large primes, it's integer, this kind of technique. So, and indeed, what those invariant, how they appear, this result for integral, the invariants appeared exactly in the argument of the platistic exponent, symmetric or something, yeah. So then I mean, for me, of course, there is sort of a general technique which goes beyond geometry, due to Anton Millet. We called such series admissible, and Millet developed kind of, he generalized our argument and developed some kind of a mini theory in his papers on the count of number of points of the finite field of the moduli of semi-stable Higgs bundles, which is another sort of geometric analog of the Nakajima quiver variety. So then I believe that there is something bigger behind of what you told us, which is more general than just, yeah.
But for what kind of for what class of functions this can be proven? I believe it's I believe those admissible series there is some kind of maybe generalizations of num sums, but the power series which appear here they are maybe num sums are limits of those, but they look more complicated. They may be more general. I'm wondering if this can be used to prove this result here. It will be very interesting.
So it's not quite num sums, but in a sense, yeah, num sums, it's a special case of those which appear. I'm not saying that your story is exactly part of this admissible series.
But again, like I don't know the proof even like in a super simple case when you consider classical Q hypergeometric series, like the very basic Q hypergeometric series. I don't know how to prove this property.
No, don't ask me about that because you see, your series, they have geometric origin, and what I mean that this geometric origin, whatever it is, for example, for our story, for Donaldson Thomas, it appears as well, Poincaré or Hodge or whatever, set polynomials of cohomology of certain moduli stacks. Or moduli spaces, if you'd like, but in our story, the symmetry group is important, so we should divide by the motive of the symmetry group. And so I cannot tell you kind of the natural generality. There are very strange things. I mean, for example, I spoke recently to people at the perimeter, to physicists at the Perimeter Institute. So there might be some kind of some factorization structures which stand behind. That's what you mentioned when you consider degeneration, your curve to compose. So there might be some factorization structure which implies that your generating function is sort of symmetric algebra of some, I don't know, you consider, because, physicists already went one step up, they consider categorification. So in the left-hand side, you have not a generating function of numbers by some whatever graded vector space, and so it's symmetric algebra of some another graded vector space for which a character is your generating function. So I don't know. I mean, it certainly resembles many things, but maybe not related to them. But when you mention this no pole result, it's exactly But so I don't know. You can also ask Anton Milit, and so maybe he can prove this absence of poles using just purely formal computations with series. I don't know.
There should be in the end. I agree. There should be some kind of geometrical argument which says that this partition function is symmetric algebra or of something. But so far, in a very simple cases like when your Nakajima variety is a point, and you study quasi-maps to kind of a point Nakajima varieties, it's possible to do it. But more generally, it's a bit not possible.
And also I have kind of very naive question. You mentioned at some point very tangentially some Yangians and other quantum groups. I mean, they appeared in the story, but they do not seem to be related to the story. But do they? I mean, with Nakajima quiver variety, you can compute this quantum cohomology, okay, theory, produce generating function, blah, blah, blah. From the same object, you can produce quantum groups. by this, I don't know, but Maulik-Konkov. But is there any relation of the series which appear here geometrically with characters of some, maybe with characters of some modules over quantum groups or vertex algebras or what? Or they just not related at all?
No. I guess you're right. So there are some infinite dimensional, graded infinite dimensional modules over Yangians and over quantum groups, such that if you take graded character of these infinite dimensional representations, you get maybe not exactly these objects, but people know how to compute limits of that object. So yeah, I don't know how to construct the whole J function, but there are some limits of J function which exactly compute the characters of the representations of these Yangians. That is true. Maybe some special.
There is a hope for people who like representation theory. Yeah, to do something here. Okay, so more questions. Well.
Okay, just a second. Sorry.
Yeah. Okay.
You expected. So you mentioned about some arithmetic properties. So in what sense the arithmetic?
So it was more of a kind of maybe of my first lecture. So when I mentioned that you have this Frobenius intertwiner, and you evaluate it at a certain points, which are called Dickmüller points, E minus so is equal to Z. Then
I see. Okay.
Characteristic polynomials of these guys is exactly like local zeta functions of some varieties. So this compute the arithmetic zeta functions of some variety. So like really a number of points on certain varieties.
Yeah, that's probably the reason I was asking you how I should understand the Z, because for modular forms we can regard them as functions complex valued and complex variable on the upper half plane. But this time I was wondering whether you were thinking that the variable Z here is on some arithmetic space, but taking values of matrix valued, but with entries inside of p-adic type of fields.
Yeah,
that's what I was kind of guessing.
Yeah, but it's above my knowledge of the subject.
Okay.
Let's say.
Okay, and the second question, quick one. So you have all these roots of units, and you have through the K-theory construction, and which will be acting on. Last time you mentioned about this K-theory acting on the cohomology of Nakajima quiver variety, which is some sort of giving the representation of the Yangjin. So does this also give representations of Yangjins at the roots of units?
Not really, because the quantum group which is acting, maybe some quantum loop group, it has some parameter, but its parameter actually not Q, but what I call H bar, right?
I see.
So this parameter H bar of a quantum, it's not Q, it's a parameter of.
That's a different parameter.
Yeah.
Okay.
But actually, there is also quantum group
with the two parameters
with parameter Q. But this quantum group, it's more related to Jan's previous question, actually. So this quantum group will act on certain infinite dimensional representations for which traces will be this J function, so like some limits of these J functions. So maybe yeah, it's supposed to be. Again, I never thought about it, but probably from this story something can be derived and some knowledge about representation theory of quantum groups at roots of unity.
Especially with Youngins, you have both H and so what the roots of units. Okay. Yeah. Well, thank you very much. I appreciate your giving a wonderful, very I learned a lot from your lecture. Thank you very much.
Thank you. Just one thing.
Okay.
I just wanted to mention, like, very briefly, that there is a story again which I completely don't understand, and it's not it's very far from me, but there is something which is called Habiro cohomology, and well, this is arithmetic thing, and this is a theory developed by Scholze and people working with him. And what they found is that there is a lot of versions of p-adic and arithmetic cohomology. There is prismatic cohomology. There are some crystalline cohomology. And those are cohomologies which are related to cohomologies over with coefficients maybe in finite fields. And so you can consider varieties over finite fields. And what they discovered is that there is some kind of, and also the RAM cohomology of some maybe things over complex numbers and so on. And I believe what they discovered, at least there is a paper of Scholze, which is called Q deformations in arithmetics, which predicts, I'm not sure if it's constructed already or it's an ongoing process, that there exists some kind of Q cohomologies, which they call Habiro cohomology. So it's a version of cohomologies which depends on Q. And this cohomology interpolates, so Q is a parameter which interpolates through all primes, in the sense that if Q is specialized to some root of unity, then this Habiro cohomology is supposed to reduce to something like prismatic cohomology associated with prime P. And again, I cannot really read these papers, but on the nose, it at least sounds similar to what I was trying to say, because
oops, seem to be stuck.
Lost connection is lost.
Probably lost the connection.
Oh,
Yeah,
that's pity. No, we can wait a little bit, but yeah, indeed, it's true that there is a kind of a work motivated by Chern-Simon theory, so it came from Zagir and his collaborator, and then later Scholze on this Habiro cohomology, but I also do not know that very well, but there is a kind of a Q version of the Daram complex and other interesting things, but and there are Q difference equations in that story, but how it is related to Andrei's talk, I have no idea. So at least it's worthwhile to look at this, because I mean, maybe Scholz papers are difficult to read, but there is his joint paper with other people, with Grafalidis. Yeah, there is, I believe, a paper which is readable. Grafalidis, Schultz, Campbell, Wheeler, Zagir. It's called the Habiro ring of a number field. You know, it's
that has a coefficient with the Habiro ring, which is the completion of integers by one mass, two mass.
The thing is that whatever Habiro ring is, its definition is its certain localization, blah blah blah. So, well, kind of.
Sorry, I didn't notice my computer died.
Your computer, but now is it? We already started internal discussion on what you said.
Okay.
I mean, this, and I said that I did not read that Scholte papers. I read some other of his papers because it's related to my work with Kapranov. But on this particular Habiro ring, it's also related to some remarkable Q-series like Chern-Simons invariants. And there is at least what I said, that I know at least one paper which is readable by Grafalidis, Schultz, Campbell, and Zagir on this Habiro ring, and so people can. So I don't know whether it's. I mean, it's just about biggest theory which includes your as a special case, or it's very special to series which appears in geometry. I don't know. Definition of Habiro ring is certainly motivated by Chern-Simons. You take just, I don't know, polynomials in Q with integer coefficients and mod out by this Q factorial, or how it is called, ideal generated by Q factorial and Q factorial, and then take a projective limit.
Yeah, that's the one.
Yeah, I've read these papers, and moreover, I guess their second paper is Grafalidis and Wheeler. It's they did it separately. It's even more readable, and it's about Q hypergeometric series, and they show that they satisfy some kind of this Habiro cohomology properties and so on. Yeah, but I don't really know what's the precise connection of my story and their story. There is certainly some intersections, but I couldn't really fully connect it.
Yeah, so then it's nice, at least for graduate students, if there are any. Today it looks like all the graduate students are somewhere. Yeah, because it's something which you can start to read from scratch. I mean, you do not need the previous knowledge. It's very basic. For example, Campbell Wheeler, he is a postdoc at IHS now, so he is not kind of algebraic geometer by education. So, and still you can do something. Yeah. So it's very interesting. Yeah. But you expect that that story is related to what you said today? Oh, well, not today, but this week.
Yeah, this cohomologies like prismatic or crystalline.
Yeah, that's the
They equipped with
arithmetic thought.
the arithmetic, but they equipped with an extra structure, namely the action of Frobenius, right? So we always have an action of Frobenius on those things. And then the prediction is that when you specialize Q to a p-th root of unity, then you get to this crystalline cohomology, and then you should be able to see this extra structure as the action of Frobenius. So in a sense, at least philosophically, it reminds me what I just discussed, right? So when I go to p-th root of unity and Q, then we have this Frobenius kind of thing acting on the cohomology. And
This looks like a kind of a crystalline cohomology theory at the roots of units.
Yeah, but
okay. Okay, well, thank you for all this information. Definitely,
whether
very
if you can kind of formally derive, you know, like if you think in terms, for example, of Grothendieck conjecture, for differential equations, and whether there is a parallel analog of it in this Habiro ring or whatever Q-deram version which Scholze considered. I don't know. As far as I know, they could not. The definition is nice, but in terms of this Q-deram, where you have also Gauss version of Gauss-Manin connection and blah blah blah, they cannot compute. I think even in the case of elliptic curves, they cannot compute anything. But maybe now they can. But at least kind of half a year ago they could not. So yeah, so it's interesting. So Andrey, thank you very much. So it's very inspiring.
Thank you.
And may I ask you to send me kind of the final corrected versions of your notes?
Oh, yeah, sure. Sure.
And so then we'll post something without typos.
Yes, absolutely. Yes, thank you.
Okay, thank you very much. Thank you.
Thank you.